The variation of the refractive index with frequency is referred to as dispersion. We can think of this in terms of how the electric field from the light will affect the particular atoms or molecules within that material. So the electric field of the light wave, remember, is just a harmonic wave with some magnitude and vector direction E. So if we apply an electric field to some dielectric material or an insulator, then what will happen is that we get a change in the distribution of electric charges in that material. So if we imagine the simplest case of just an atom where we've got a positive nucleus and a negative electron cloud, if we then apply an electric field, then what will happen is that the electron cloud will get distorted by that electric field. Okay. So what we then create is an electric dipole, because we have a plus and a minus end to that little distribution there, and that gives us an electric dipole. That electric dipole will have a certain moment, and if we then change from a positive direction for the electric field to a negative direction, then what has to happen is that this cloud of electrons has to switch from this side over here to the other side of the nucleus. So we'll have a certain moment that it takes a certain degree of force for that to happen. The degree of separation that we get here is referred to as the polarization, the electric polarization. Be careful, this is not optical polarization. We'll talk about that a bit later. So the electric polarization which is produced depends on the size of the electric field and the direction and the electrical properties of the material. We can consider different groups of materials, for example, polar molecules. So molecules which have a positive end and a negative end. One of these is water, H2O. The hydrogen end is positive with respect to the oxygen end, and so with thermal agitation, if it's just under normal thermodynamic equilibrium, then the molecules will be completely randomly orientated. If we were applying an electric field across that, then the positive and the negative ends would start to line up, and what we get is the molecule actually rotating around to line up with the field, the electric field. So that's referred to as orientational polarization. Here. So here we have our molecule of water. We have a positive and if we apply an electric field to that, then what's going to happen is the whole molecule is going to rotate to try and line up with that. So we have orientational polarization here. Now, because we've got to move the whole molecule, the whole thing has to spin around, then compared to the next couple of categories, you have a fairly high level of inertia, and so it can't spin around because it's got a relatively large mass compared to just an atom or an electron, for example. Because it has a relatively large mass, it has a relatively high inertia, and it can only follow relatively low frequency electric fields. So if we're trying to drive the system with its plus end and minus end, and we're trying to spin it round and then back again, then you can imagine that with a certain degree of inertia that's going to be possible at low frequencies but not at high frequencies. Ionic crystals, so these are solids where you have, for example, salt, sodium chloride, and one of those ions is positive and one will be negative. And what we have then is ionic or atomic polarization. So here in our ionic crystal, we have the sodium and the chloride, sodium, and chloride. Okay. And those are separated again by some distance dependent on the structure of the actual solid. If we apply an electric field here, then what will happen is that the electric field will drive these sodium and chlorine atoms perhaps together and then apart, depending on how the electric field is applied, either in one direction or in the other direction. Remember, it's just a sine wave, so it goes positive, negative, positive, negative. Okay. So here we've got individual atoms, or ions, really, ionized atoms, which we're trying to get to move around. These are lighter than an entire molecule, and so these can respond to higher frequencies than the polar molecules. The final case is if we have just an atom on its own, or a group of atoms, obviously. Then here we have a nucleus and an electron cloud, and the mass of an electron is significantly, many orders of magnitude smaller than the atoms here and the molecules there. And so this is the smallest mass and the smallest inertia, and so this is a system which can respond to the highest frequencies. So this electronic polarization, because it depends on the electrons, is the one which is most appropriate for optical systems. Remember, we're oscillating at 10 to the 14, 10 to the 15 hertz, depending on wavelength frequency. Now, can we come up with some sort of idea or a model which will describe how this system behaves? What we're doing is we're applying a force, an oscillating force. We've got a system which is going to give us some sort of response. It's going to be driven into oscillation. There will be some damping and there will be some oscillatory behavior exhibited. So we can conceive of this as being like a classical driven damped oscillator. And we will assume that each electron is bound to the nucleus by some imaginary tiny little spring, and its restoring force will be dependent on the mass of the electron, the frequency at which the resonance frequency that it has for that spring, and the distance that it's being stretched. Okay. So let's have a look at that. So for our electron cloud, our whole electron cloud is moving backwards and forwards, oscillating backwards and forwards, as the electric field is driving it into oscillation. And we can think of this then as a nucleus in the middle here with a positive charge, and each of these electrons is attached to the nucleus by some sort of spring. So we have a mechanical oscillator description of what's happening inside this this atom, and we have our electric field, which is providing a sinusoidal varying force, which is pulling these electrons in one direction or another. So for the whole model, then we can compare it to driven damped oscillators that we've seen before, and hopefully the equation, or bits of this equation, will not be a surprise to you. So if we just think about this part here, then you'll see that we've got a natural frequency, we've got a driving frequency, and we've got an imaginary term here which is representative of the damping in the system. Okay, so it's just a driven damped oscillator. This is a solution that you would normally see for a driven damped oscillator, but it's a wee bit more complicated because we're dealing with atomic systems or imaginary springs in systems, and we have to think about the mass of the electron and the charge on the electron, QE, as well. Okay. So a refractive index depends on the behaviour of this driven damped oscillator. If we think about what we get in terms of behaviours that are exhibited by driven damped oscillators, then we have things like resonance frequencies, we have damping, we have critical frequencies, and so on. And we'll see all of those exhibit themselves in the optical behaviour of insulators. So the damping force is proportional to the oscillation speed, omega, and the energy that's being lost will be lost here in this part of the equation. So the damping force is given by the imaginary part of that equation. Now, if we think about what damping is conceptually, we put energy into the system to try and get it to do something, and that energy gets wasted in some way, it gets lost in some way, or soaked up by the system in some way. In optics, we refer to that as absorption. So the light is being absorbed by that particular material. So when we see absorption in a material, it means that we can see then that we have some damping in the system, and therefore that we have a more complicated version of the refractive index. If we don't have any absorption, if we have a material which is completely transparent, it doesn't absorb any of the light that passes through it, then we can see that this extra term here, the complex term, will be zero, or effectively zero, or so small that we don't have to worry about it. So this model that we have, this equation, is only good, again, for low pressure gases. When we get to materials such as solids, liquids, or more dense gases at higher pressures, for example, then we have to take into consideration the effect of nearest neighbours. So the electric field, which is produced not just by the electric field that's coming in, but if we apply an electric field here, then we get an electric field produced, a counter electric field which is produced within that atom as well. Remember, if I want to make an electric field, I have to take some positive charges and some negative charges and separate them out, and that's how I get my electric field. So here I've applied an electric field, I've separated out the charges, and I've created an electric dipole, and that then creates its own electric field in here. If we have a dense material, then that internal electric field that's being produced within the dipole, the electric dipole field, we need to worry about, well, what effect will that have on its nearest neighbours? If the nearest neighbours of atoms or molecules are close enough, then it will experience not just the electric field of the light coming in, but also the electric field, the dipole field of the atom itself being polarised. If that's the case, then we can rearrange the equation and rewrite it as this expression here. I'm not going to do any derivations of this expression, just a sort of hand-waving argument as to where it comes from. So don't worry about being able to make a derivation going from equation 6 to equation 7. The same sort of shapes, resonant frequencies, natural frequencies, driving frequencies, and damping terms. And what we're going to do now is we're going to look at this equation and see, well, if we start stripping out bits of this equation, what does that mean physically? What does it mean in terms of what we see? Well, we've already said that if we don't have any absorption, then the refractive index is real, and this term, this imaginary term here, is essentially negligible. So if the difference between the resonance frequency, or the natural frequency, and the driving frequency is big, so in other words, as long as you stay away from resonances, then this number is going to be much bigger than that number, and so we can ignore that number in our equation. And it simplifies then to this form here. So colourless and transparent materials which don't have any strong absorption in the visible region, will therefore we can model them using the equation, the simplified equation here. For most materials, the absorption, for most transparent materials in the visible, the absorption happens somewhere in the ultraviolet, usually. And so we don't have to worry about that unless we're dealing with ultraviolet light. What we'll see here is how does n depend on frequency? If we increase frequency, then we see that the value of n will increase with frequency, and that's referred to as normal dispersion. So as omega gets bigger, then the difference between these two, omega naught j and omega, gets smaller, and that means we're dividing by a smaller number, and so the whole thing starts getting bigger. Okay, so increasing frequency as we approach the resonance frequency, the refractive index is going to get bigger, and I'll show a graph of that in a second. As we get towards the resonance frequency, then the damping term is going to dominate, and the omega minus omega naught term here is going to be very small compared to the damping term. And we refer to those regions as absorption bands. So these are regions where there is strong absorption. As I say, for insulators, that's mostly in the UV or the vacuum UV, the VUV. If we're very, very far away from the resonance, if the resonance frequency or the natural frequency is much, much, much bigger than omega squared, then the equation can be simplified even further, and it becomes essentially a constant. So for frequencies which are very small compared to the resonance frequencies, then the refractive index will tend towards some fixed. Here are some graphs. This is wavelength. Increasing wavelength means decreasing frequency. So if wavelength is increasing there, then our frequency, nu, is increasing in that direction. And these are various different types of glass materials that we would commonly find in optical systems. So as you see, if we go to very long wavelengths or very low frequencies, then asymptotically the values of the refractive index approach a constant value. And as we go up in frequency, shorter wavelength, then we can see that the refractive index starts to increase. Oh, sorry, I'm trying to erase that. Starts to increase as we head towards one of those resonances. As we hit the resonance, then obviously this shoots off towards a purely imaginary number.